The molecules are rotating. Yes, you can see children, they are rotating also. They are vibrating also. So, they are possessing different types of, see this children, vibration. So, they possess different types of kinetic energies and also potential energy. Now, let us see what these total energies add up to. The total energy of the system is called its internal energy. Okay, children? The total energy of the system is called its internal energy. This total energy is the sum of the kinetic plus potential energy, where the kinetic energy is a combination of the linear, rotational and vibrational kinetic energies. Okay, children? So, kinetic energy is a combination of linear, rotational and vibrational kinetic energies. When these all energies add up with potential energy, the sum is called as the internal energy. The heat energy that is supplied to a substance is shared by the molecules among the various forms of energies. So, whatever heat we are giving to the substance, it is shared among the molecules with different forms of energies. Some molecules are under linear motion, some molecules are under rotational motion, some are in the vibrational motion and some have potential energy. So, the energy that is given to the substance is shared among the molecules of different forms of energies. The rise in temperature is high if maximum heat energy is utilized to increase the linear kinetic energy. This is an important point here, children. When does the temperature increase more? When is the temperature high? When the more amount of heat energy is going to the linear kinetic energy. Okay, children? That is, it is helping the particles to move from one place to another place rather than rotation or in vibration. Children, we know that temperature and kinetic energy are directly proportional. Yes? So, when you are heating the substance, temperature increases and hence the kinetic energy should also increase. So, if the share is more towards the linear kinetic energy, then the rise in temperature is also more. This sharing of energy varies from substance to substance. Hence, the specific heat is different for different substances. This is the reason, children, why specific heat of different substances is different. It is an important question, children. You have to make a note of this and learn it. Now, children, let us see applications of specific heat where we observe them. Look at this image, children. Yes, it may be reminding you of what you have learnt in your geography, the convection current. Yes. So, children, what is happening? Due to the heat of the sun, the land gets heated up. The ocean does not get heat as fast as land because the specific heat of the water is higher compared to the land mass. Yes, children? So, land gets heated up very fast. So, what is happening here? The warm air is rising up. The warm air is rising up here. Okay, children? And what is happening to the warm air? The warm air is replacing the colder air on the water surface. Is it clear, children? Because we know that heat flows from hotter bodies to the colder bodies. It is the nature of the heat to flow towards the lower temperature regions. So, because ocean is still cool because of presence of water, because of high specific heat of water, heat from the land flows towards the ocean and the cool breeze of the ocean is received by the land surface. It is a replacement, children. Warm air reaches the ocean and cool air reaches the land. So, with the help of, because of the high specific heat of water, the ocean water or the sea water does not get heated up faster. It just retains the heat with itself, but it does not show a rise in temperature. So, here warm air moves from land to water bodies and cooler air moves from water bodies to land. In this way, the specific heat of water helps in controlling or optimizing the temperatures on Earth's surface. Then, children, the sun delivers a large amount of heat energy to the Earth daily. The water sources on Earth absorb this energy for maintaining a relatively constant temperature. So, the water surfaces, children, because of their high specific heat capacity, they do not show an immediate rise in temperature. They retain the heat inside them. So, we call them as, the oceans behave as heat storehouses for Earth. So, what is happening, children, here? One more thing. When they are receiving heat, this heat is transmitted to the polar regions from equator. So, we know, children, equator is always very, very hot and the polar regions are always very, very cold. So, heat is flowing from the equatorial regions to the polar regions. Okay, children? So, in this way, overall a constant temperature is being maintained on the Earth's surface, so that the hotter regions don't remain hot for a long time and the colder regions don't remain cold for a long time, which is helping in the sustenance of life. Let us see two more examples of specific heat, children. When the watermelon is brought out of the refrigerator, it retains its coolness for a longer time than any other fruit. We know this, children. If you keep our watermelon in the refrigerator and other fruits, bring them out together after putting in for the same time, then we see that watermelon will remain cold for a longer time compared to any other fruit. Why is it so? The name itself, we know, watermelon contains a large amount of water compared to any other fruit. Hence, it will retain the coldness for a longer time owing to its high specific heat value. Next example, we all love samosas, isn't it, children? We all love samosas, kachoris, all snack items. So, a samosa appears to be cool outside, but when you take a bite, sometimes your tongue gets burnt. Why is it that it appears hot outside, it appears cool outside, but it is hot when we eat? Children, it is because that the substances present inside the samosa, the vegetable curry that we stuff inside the samosa, have more specific heat compared to the outer surface coating. Right, children? So, these are the applications of specific heat. Next, children, we are going to learn about the method of mixtures. As I told you in the introduction, mixture is a combination of two or more samples of the same substance but at different temperatures. So, here we are considering two samples of the same substance with different masses and different temperatures. Let M1 be the mass of the first sample, M2 be the mass of the second sample, T1 is the temperature of first sample and T2 is the temperature of the second sample. Such that T1 is greater than T2, T1 is greater than T2, and T is the final temperature of mixture. When we mix these two samples, they both reach to a common temperature which is given by T. And how is this T going to be, children? It will be in between T1 and T2, yes or no? It will be in between T1 and T2, such that T will be less than T1 and T will be greater than T2. Let us say S is the specific heat of the substance. So, here what is happening, children, in the mixture? So, heat lost by the hotter sample Q1 is equal to M1S into T1 minus T. So, heat gained by the cooler sample is equal to M2S into T minus T2. Q2 is equal to M2S into T minus T2. We know that heat lost by the hot sample is equal to heat gained by the cooler sample. Suppose if the heat is not going out, it is in the system, then the heat lost by the hotter sample is equal to heat gained by the cooler sample, so that Q1 is equal to Q2 and M1S into T1 minus T is equal to M2S into T minus T2. On simplification, we have this formula of the temperature of the mixture, which is given by T is equal to M1 T1 plus M2 T2 by M1 plus M2. This is the temperature of the final temperature of the mixture. Based on this, we will write the principle of method of mixtures. Children, you have to learn this principle. When two or more bodies at different temperatures are brought into thermal contact means, children, there is a possibility of exchange of temperature. So, when two or more bodies at different temperatures are brought into thermal contact, the net heat lost by the hot body is equal to the net heat gained by the cold body. So, net heat loss is equal to net heat gain. So, when a hot body and a cold body are in thermal contact with each other, then there is an exchange of heat in between them. The hot body loses the heat and the cold body gains heat. So, net heat loss is equal to net heat gain. This is the principle of method of mixtures. So, we have come to a conclusion of this session, children. Before closing, let us see what we have learnt in today's class. The specific heat of a substance is the amount of heat required to raise the temperature of unit mass of a substance by 1 unit. So, we have seen specific heat value is different for different substances. It depends upon the sharing of heat energy among different types of internal energies. The final temperature of the mixture of different samples is T is equal to M1 T1 plus M2 T2 by M1 plus M2, and the principle of method of mixtures, net heat loss is equal to net heat gain. Heat lost by the hot body is equal to the heat gained by the cold body. Children, try to answer these simple questions. Why specific heat is different for different substances? How does the specific heat of water help in optimizing the Earth's surface temperature? What is the principle of method of mixtures? And define the internal energy of a system. So, children, I hope you understood the concepts clearly in today's class. So, children, I hope you have understood today's class and learned the concepts. Children, try to complete the notes and also complete the worksheets provided in the SCRT website. Happy learning, children. Bye.